Good morning. Welcome to Krishna's classroom. We shall pick the threads from where we left it last time. And if you recall, I was trying to explore the evolution of the definition of continuity in the context of metric spaces and eventually in the context of what are called topological spaces. If you recall, see, you have the real line R with the usual D defined as, so RD is a metric space. Then you see RD a metric space. Here what we have done is we have explored the fundamental properties of mod x minus 1. And then we made use of that and then generalized it to an X non-empty set, X with a D. Now D is metric. I am not going to repeat the definition of a metric. So it becomes a metric space. Then of course the next stage is we use, now let me just say, we have what are called neighborhoods. Which are open balls. Then this leads to the concept of what are called open sets. And then the fundamental properties of open sets. Fundamental properties of open sets, namely empty set is open, the whole of X is open, then arbitrary union of open sets is open, and finite intersection of open sets is open. Then we, in the topological spaces, we start with an X and a collection of sets, subsets of X, which you call the topology, provided a certain conditions are satisfied. Now here, what we choose as the conditions is the following. X belongs to tau, empty set belongs to tau, then arbitrary union of sets in tau is again an element of tau, and finite intersection of elements in tau is an element of tau. Those were the fundamental properties that we established in the case of open sets for a metric space. So there may be a situation where a metric may not be defined on the space, but you may have a more general scenario which leads to the so-called topological spaces. Okay, so this is the chronology in which probably, or the sequence in which the generalization has happened. Now then we look at the concept of continuity. First formulation in R. There are two formulations that you come across. That is, a sequence xn contained in R, x belonging to R, then f from R to R is continuous if xn converges to x, implies the sequence fxn converges to the value of the function at x. Of course, you need not be, this is not defined only for functions from R to R, but probably from a subset x of R to R. Okay. So this is through the convergence of the sequences we define it, because we are very familiar with convergence of sequence of real numbers. Now this is generalized to in terms of distance function, namely metric. So you get this notion, that is xn was xd metric space xn contained in x, x belongs to x if converges to x, so we take f a map from x, then we say f is continuous if implies, this is in the sense of the metric, the sequence fxn converges to the value of the function at x. So that's the definition of continuity that we have straight away generalized. Then going back into R, we have back in R, we have we say that f is continuous at x belonging to R if given epsilon positive, there exists a delta which may depend on epsilon, even on x. In fact, it may even depend on x. Positive, such that mod x minus y less than delta implies mod fx minus fy is less than h. Now this is the definition. The other definition that we have for in R, and consequently the analogous statement is that d of, see, modulus is now replaced by d of given epsilon positive, there exists a delta positive such that d of minus x comma y, distance from x to y, plus d of less than epsilon. Of course, y belonging to so you see that this modulus is now replaced by the distance function. Okay, that's a generalization. Okay, now what do we do? Let us analyze this. If you analyze this, okay, in this we have done in elaborating last lecture to go through, but I am just repeating because it is important. It's important to see the evolution, stress on this fact. Okay, so this statement is equivalent to the following. Let u be, or what you call b x delta be a set of all y and b less than epsilon. So these are the two definitions of the sets. Then the above statement implies f of so that is the rewording of the whole thing. Okay, right. Now, what we can do is, see, this is only for neighborhoods that we have said, and one can show that as we shall do now. If this is equivalent to the following. F is continuous is if for every open set U V open in X, because I am talking about mappings from X to X, okay, for the time being, but you can always generalize it. Yes, I am going to do so. Open in X containing X. There exists an open set U contained in X with containing Fx. Such that f of u contained in for each v there is a corresponding u. If you want, you can be there exists a corresponding open set, then you say f is continuous. So that the last one can be easily carried over to the statement I have made just now, or this statement is accepted as the definition of continuity of a function I want to make some remarks here, because you see that where x tau is a topological. So the difference is going to be that, see, for any U containing, for any V containing Fx, where V is an element of tau, okay, there exists an element of U in tau such that containing X such that f of u is containing. So these are the things. That is, f is from x to x. X tau is the topological space. Now, continuity at is defined as x belonging to V belonging to tau such that Fx is an element of V there exists for any V, I should write, there exists U belonging to tau containing such that this is the systematic evolution of the definition. You see that the concept of open set in a metric space uses the metric, whereas you don't have any such thing. All that you have is just a bunch of subsets of X with certain properties which you call a topology. Okay, so if you carefully examine how the thinking has gone, starting from our experience of working with real numbers and functions defined from R to R, and going through metric spaces and eventually coming to the most general form, namely topological spaces. So that's what I was trying to examine in my lecture last time. So, okay, so let us now give the statement of the theorem. Of course, I am going to do this only in metric spaces. Okay, the equivalence of the various statements I have made, which are apparently look disconnected, we prove the equivalence of the various statements. So let me just give the statement of the theorem. The theorem let x dx comma y dy be metric spaces. Of course, dx designating the metric in x and dy designating the metric in y. Let f be a map from x into y. So let f be a function from x to y. Then the following statements are equivalent. The following statements are equivalent. What are the statements? The statement A is f is continuous x. Now that is, this is the statement. You know that we call the definition of continuity, the sequential definition of continuity. Xn converges to x then f of xn, the sequence f of xn converges to f of x. Xn converges to x implies fxn converges to x. True for all such fxn which converges to x. Take out this. If xn converges to x implies fxn converges to f of x. Okay, this is of course dxn x going to 0, that is dx goes to 0. That's the number. Okay. Now the statement B is given any epsilon positive, there exists a delta positive. Now this delta may depend on epsilon as well as x, such that dxy less than delta implies okay. C given an V containing fx given an open set V containing fx we can find an open set U in X containing X such that f of u so these are the three statements. It is done in metric spaces. We shall prove the equivalence of these three statements. So once we prove the equivalence of these three statements, any one of them may be accepted as the definition of continuity point in the domain. So what we are going to prove is the equivalence of these three statements. What do we mean by that? Okay, I want to spend some time a little bit elaborately on these kind of aspects. Okay, I was talking about a different thing, namely once we prove all this, see, the third statement, that is C, is something that can be carried forward into a topological space. Although both A and B makes absolutely no sense in a general topological space, unless it is a metric space. You know that every metric space is a topological space, but not the converse is not true. Okay, so C gets accepted as the definition of continuity of a function at a point in the domain, whereas any one of them is equally valid in the context of a metric space. Okay, the purpose of solve or proving this theorem is essentially to show the equivalence of these statements in a metric space and the possibility that any one of them can be used as a definition of the continuity. Okay, now before I start proving the equivalence, I want to make some remarks about the method of proof, because that is important. When this is in a very general context I am talking about. Therefore, I think in various situations you will come across this kind of results, and you should clearly understand what are the possible avenues of. Okay, let me ask the following. Suppose U is a some general remarks on. So let me just write. And the proof strategy. One should understand this very clearly, because there are many situations where you come across, and this is an area where a lot of confusion exists in the minds of the students. That is why I want to spend some time. Okay, let U be a universal set. Let P and Q be two properties satisfied by elements of U. Okay, here the metric space is the universal set that we are taking. Now, if you look at the first statement, that is xn converges to x implies fxn converges to x. That's a property that's valid by elements in x. Okay. So now I'm just in the most general form. Okay. So what do you have? Let me fix the notation to begin with, and then come to the statements of the theorem. Yeah. So let capital P is a subset of U defined by set of all x belonging to U such that x the property P. And so also Q denote the subset the property. Now let us look at the following statement. Suppose we want to prove that is, what is the meaning of this? If x, that is, if x satisfies P, then x satisfies Q. That is, the set P is contained in Q. Okay, let me draw a picture. So you have, suppose this is the set P. So when you say P implies Q, that means if an x satisfies P, then it is an element of Q. This is the relation between the sets P and Q. Now you observe that from basics of set theory, P implies P contained in Q if and only if Q complement contained in P complement. What is Q complement? Q complement is this. This is Q complement. Now what is P complement? P complement is this one, this whole thing. So you see that if P is contained in Q, then Q complement is contained in P. So they are equivalent statements, because you know that P complement is P. Okay. Therefore, this statement is clear. Okay. Now, what is the meaning of P complement in terms of the property P? So, P complement X does not satisfy P. What is the meaning of that? So, Q complement is likewise Q. That's the statement. Therefore, what is Q complement? P complement implies P, then X okay, which is the same as, so Q complement Q not true or true. That is a negation. Okay, right? So you have this relation. P implies Q if and only if P is contained in Q, if and only if Q complement is contained in P complement. That implies not Q okay, right? So not Q implies not P, means Q complement is contained in P complement. If and only if P is contained in Q, so you have this statement, this statement, this statement. There are 4 statements. Okay. So instead of proving P implies Q, it is sufficient to prove that not Q implies not P. They are equivalent. Okay. So P implies Q is equivalent to not Q not P. Okay, so this is what you call through negation you prove the same result. Okay, right? Or by the method of contradiction, and of course then of course how you prove this? Through negation you prove this. So instead of proving P implies Q, you prove not Q implies not P. Sometimes this part is easier than proving this. We shall encounter a similar scenario while proving our theorem. Okay, so with these basic remarks, and I think you should very carefully analyze this. Okay, because that will give you a lot of insight into in developing proofs. Sometimes P implies Q may be difficult to prove, but not Q implies not P may be easier. Then you resort to that, okay, which is equivalent. Okay, so let us now come down to prove this result. Try to understand what are the steps that we follow. So what do we have to prove? So the proof of the theorem. Strategy. What we prove is A implies B, comma, B implies C, and C implies A. Then you can get, if A implies C, A implies C because this is an equivalence. If A implies B, B implies C, then A implies C. If this implies is an equivalence relation. So A implies B, sorry, it's transitive. Therefore, A implies C. So implies is transitive. Therefore, A implies B and B implies C implies A implies C. And then if you prove C implies A, then you have A implies C and C implies A. Likewise, you take any pair of them and show that one is equivalent to the other. Okay. So it is enough to prove this chain. So we first prove A implies B, then we prove B implies C, then we prove C implies A, then you have a cycle. This is a cycle. Okay. NISER. So that's a strategy. That's a strategy that you often resort to while proving this kind of equivalent statements. Okay. So let me start with, so we prove this first. So assume what does it mean? Assume what does it mean? That is, for f is continuous, okay, that is, for any sequence xn converging to x in x, the sequence is contained in, converges to f of x in y. That's assumption. Okay. Claim B. What does it say? It says where x is a delta positive such that p of x y less than delta implies p of epsilon. Here, of course, what you have is this. So you have dy, here you have dx, this is the metric, and f is a function from x to. What does it say? It says given epsilon and a neighborhood of b fx epsilon, this is bx x epsilon, there exists a neighborhood this is b, there exists a delta neighborhood of x such that this whole thing gets mapped into this is the image of okay, this whole thing gets mapped into this. Now it is a bit more clear in this case of a function. So you take a function f from R to R. Now you can draw the graph of the function R, and you can draw the graph of the function. This is say x. For x belonging to R. Okay. So that's an arbitrary point. Okay. Suppose you take a point x. Or in the domain. So you are taking x as a point here. Now let us pick So F is a map carries this into S. That's how you get Fx. Now what does the statement say? What is the neighborhood of epsilon neighborhood of Fx? So given epsilon or given an epsilon neighborhood of Fx, what is that? That is Cn or B Fx epsilon is equal to such that the distance from y to for a fixed x. Okay, that means which is equal to the interval epsilon. So this is the interval. I will mark this. So this is the interval. This is Fx minus epsilon plus epsilon. This is, so it is the interval Fx minus epsilon to Fx plus epsilon. Okay. Then what does it say? It says there is a delta neighborhood of x so this is from x minus delta to x plus delta with the property that the delta neighborhood gets mapped into the this is the image of the delta neighborhood. So given an epsilon positive and an epsilon neighborhood of Fx, there exists a delta positive with the property that the delta neighborhood of x will get mapped into the epsilon neighborhood of Fx. Okay, right? Now you see that it is quite possible, as it is clear here, there are other points which get mapped into Fx. Okay. So there is some x1 here which also gets to Fx. So there may be several points. For instance, if you take the graph of the function sin x, so this is sin x. Now you see that it's not just an x, this is an x1 that gets mapped into Fx, sin x1, and this is also the same as x2 gets mapped to sin x1, here x3 gets mapped to sin x1, x4 gets mapped to sin x1. What is that? This is actually x1 plus see x1 plus pi is what? This is 0, this is pi, this is 2 pi. Okay. So you see that there are two different points here, x1 and x2, belonging to getting mapped to x1. So if x1 lies between 0 and pi, then there are, and if it lies between 0 and pi by 2, if x lies between 0 and pi by 2, then you have an x2 that lies between 0 and pi, which gets mapped into the same sin x1. Similarly, you have other points, as you can see here. Therefore, there are several points which gets mapped to this point. But what we say is that we are only interested at some point x. So you see that there may be some x1 which may get mapped here. There is some another x2 which may get mapped to this. All this may go to which get mapped. There may be multiple points which get mapped. We are only examining the continuity at some point. In that case, you are talking about a neighborhood. Okay. So you start with a neighborhood of fx. Then there is a neighborhood of x which under f gets mapped into the epsilon neighborhood of x. This is the, then you say the function is continuous at, the function is continuous at. Okay, so we shall now go on to prove this. Okay. Okay, now let us try to work out the proof. So what we are up to is, so we are going to prove, but what we use is, you know that this is if and only if B not B not A. Okay. So what is A? The statement A is Xn converges to X implies the value of the function X. This is the statement A. The statement B is, so okay, statement B is such that such that sorry, f of B okay. This is the statement. So we are going to prove the equivalence of these two. Okay. Let us write down the negation of each of the statements. What is the negation of B? So given epsilon positive, there exists a delta such that this is true. That means for every epsilon positive, there exists a corresponding delta positive. This is the statement. Therefore, the negation of this is going to be, if you negate this, what does it say? That for some epsilon positive, there exists no delta such that, what do we have? We have f of b delta. What does this mean? This means the following. Like this, such that dy of dx of x of so this is the statement that okay. This is true. Okay. So what is the negation of this? This is statement B. Negation of B is the following. This you have to understand very clearly. Negation of B is there exists for every will be replaced by there exists an epsilon positive such that for every delta positive, this will complete this. Note this. Okay. For every will be replaced by there exists some epsilon positive such that for every delta positive, there exists a delta positive will become for every delta positive. This is not, that means dx x y less than delta does not imply so that is the method of contradiction. So the method of contradiction, this is okay. So the negation property. So we assume E is not true. Okay. Then what does one get? That is, for some epsilon positive, there exists no delta required property. Okay. Since no delta exists, we start working with a particular delta. Okay. So choose one by n. Then what is the statement that we have made? Then there exists an x prime belonging to x such that d x prime is less than epsilon, but dy of is greater than or equal to . So you choose delta equal to 1 by n, then what we have is, then there exists an x prime belonging to x such that dx x prime is less than epsilon, but this is not true. Okay, that means this is not less than 0. That's the meaning. Let's say write as greater than or equal to epsilon. Call x. Okay. Now what do we have to prove? We have to prove the negation of this. Okay, xn converges to x implies fxn converges to fx. So we want the negation of this. What we want is that there exists an xn that converges to x, but this does not converge to fx. So that's what we want to prove. So xn x prime you write as xn. Now we have this for all n belonging to. That means corresponding to each n you can find n xn. What about this property of this? Then what we have is that dx x xn converges to 0, because this is less than 1 by n. As n tends to infinity, it goes to 0. That is xn converges to x. But what about fxn? Look at this now. See, consider fxn. The sequence fxn. And what do we have? We have dy of is greater than or equal to x. Okay? For every n. What does this mean? This implies the sequence of xn does not converge to f of x, because the distance between fx and fxn will always remain a positive distance. Therefore, you cannot have fxn converging to x. That means that is A not true. So we have proved that if B is not true, then A is not true. B is not true, I think you should sit down and analyze this proof. Okay, sort of arguments which you will be using every now and then. What is the consequence? Not B implies not A, or equivalently A implies, okay, so that's the proof of this theorem. So this part one should look at very carefully. Another two cases, that is B implies C and C implies A, simply it is direct. Okay, so we are going to go to the proof of B implies C and C implies C. So one should learn how to write the negation. It's important. So we prove this is the one that we are going to prove next. Assume B. That is given epsilon positive, there exists a delta positive such that the delta neighborhood of x gets mapped into the epsilon neighborhood of fx or f of epsilon. That is the assumption. Now we have to prove that. So the statement C. V U contained in U such that f of U now take an epsilon neighborhood of This is containing fx, where x is a u containing x, such that this whole thing goes into of. This is what you want to prove. Okay. So what do we do? Why then what could we say? Since V is an open set in Y containing Fx, Fx is an interior point of V. That is, there exists an epsilon positive such that B is contained in then by B, which we have assumed, there exists a delta positive such that f of Bx delta is contained in B of epsilon. So choose U to be equal to B x delta, because you know that open ball of delta positive and is an open set X containing X. Therefore, what do we have? So, to start with an open set containing fx, then there is a neighborhood of fx in completely contained in V, and you see that that's an epsilon neighborhood. So there is a delta neighborhood of x in capital X, which is a ball of radius delta, with the property that that ball of radius delta is completely mapped into B fx epsilon. That means B fx epsilon is contained in V. Therefore, what happens? If you choose U as the delta neighborhood of X, then the entire delta neighborhood, that is U, is completely mapped into the epsilon neighborhood of fx, which is contained in V. Therefore, fu is contained in. That's our argument. Therefore, we have, if you assume B, then you have C. Now, to conclude the equivalence of all the three, all that we need is, we assume C and then prove that A. Now C, so assume C. Now I don't want to repeat it. So let Xn be a sequence converges to X. Okay. Then we have, so what do we want to prove? The sequence fxn that is dy of goes to 0. This is what we want to. So what we do? So we have to show that this statement means that given epsilon positive, consider that is the epsilon neighborhood of fx. Then B is open. Then by C, there exists an open set U contained in X such that and f of u is contained. That is by the assumption C. Now since U is open, draw it. We have this is Y, this is X. Now this is the point X, Fx. What you do is take B and this you take as V, then you have some neighborhood U of X such that this gets mapped into Fu. Okay, so U is open means there is a R positive such that for every n greater than or equal to n, xn belongs to exn, which implies f of xn belongs to f of that is, this is the R neighborhood, that XR, which is contained in Fu for every n and this implies, see, this is true for any arbitrary choice of R. Okay, sorry. So we have this. This implies, what does this mean? This Fu is contained in F of therefore that implies the sequence Fxn converges to which implies, so we started with an arbitrary sequence xn that converges to x. Okay, then we have proved that if the sequence Fxn converges to x, implies F is continuous that is the original definition for any arbitrary sequence xn that converges to x. fx and converges to fx. Okay. Therefore, we have proved A. Anyone should sit down and analyze these three proofs. So that actually completes the proof of the theorem. Okay. I hope I have tried to make all these ideas clear, and we should also spend some time sitting and thinking about this. Thank you very much.